Unit Operation Classroom, and today we are discussing a problem on Kirchhoff radiation law. My name is Shekhar Bhattacharjee. A body is placed inside a body. This body is placed inside a perfectly black enclosure. So let's call this as a perfectly black enclosure and is allowed to reach thermal equilibrium. We'll discuss what it means, what it means by thermal equilibrium. According to the Kirchhoff identity, which one of the following is equal to the emissivity of the body at this given wavelength, lambda? Okay. So as I said, so we'll assume this to be a black body, and of course, this is my gray body or any other body we're assuming. So of course, from the black body, there is a radiation from all possible direction here, falling on this body. And of course, and if we assume that E lambda B, that's a black body emissive power at a certain wavelength lambda, then whatever this the radiation energy falling on this particular body at a particular wavelength, because it is falling at all possible wavelengths, but at a particular wavelength lambda, if this is the amount of energy that's falling on it, part of it is absorbed. Let's call this as alpha lambda, and part of it is reflected. Let's call this rho lambda, and part of it is transmitted, right? And for now we are assuming that it's not transparent, so we are assuming this to be equal to 0. Okay, so this is not applicable. So, where alpha lambda is, of course, the absorptivity at that particular wavelength, rho lambda is the reflectivity at the wavelength, and tau lambda is the transmissivity at wavelength, and we are assuming this to be equal to 0. Okay, so this is the situation, and we have to find out what is the emissivity of the body, of this body, at a certain wavelength. Okay. So, as we said, this is going to be perfectly opaque body. We're assuming this to be equal to 0. There is no transmissivity is equal to 0. So, at thermal equilibrium, at any wavelength lambda by the body, amount of energy absorbed at lambda, of course, it is all possible lambdas. It is emitting radiation. So, at amount of energy absorbed by the gray body is, of course, is equal to alpha lambda E lambda B, which is this one right here. Okay, where it is the total amount of energy falling on this body, and part of it is absorbed, right? So that's the amount of energy absorbed. And the amount of, so at thermal equilibrium, the amount of energy absorbed must be equal to the amount of energy emitted by the gray body. That's what is meant by thermal equilibrium. So that must be equal to E lambda, right? So, well, if we equate these two, then we get alpha lambda, which is the absorptivity, is equal to E lambda divided by E lambda of the black body. And this, by definition, is the emissivity of the gray body, of emissivity of this body here. Okay, and alpha lambda is the absorptivity of the same body here. Okay, how is this defined as this one? Because E lambda, epsilon lambda, which is the emissivity at a certain wavelength, is equal to the radiation emitted by the body divided by the radiation emitted by a black body at the same temperature, which is this one right here. So, at thermal equilibrium, absorptivity of the body at a certain wavelength must be equal to its emissivity at the same wavelength, right? So that's what the Kirchhoff law is. In fact, it says for a body at a temperature equilibrium with its surrounding, its emissivity and absorptivity are equal. Okay, so if that is so, we can see the emissivity of the body at a given point must be equal to the absorptivity of the body at the same point. So this must be the correct option. Okay. Now, reflectivity, of course, this is not true. In fact, alpha plus rho plus tau equal to 1. Absorptivity, this is the alpha plus rho plus tau is equal to 1. Absorptivity, this is reflectivity, and this transmittivity. Even we have assume this to be equal to 0, so alpha plus rho is equal to 1. Okay, it is not alpha is equal to rho. Right, so this option is not correct. Stefan Boltzmann constant, of course, in total emissive power. So we'll discuss that when the opportunity comes. And of course, this is not going to be equal to 0. So this is not correct. This is not correct. This is not correct. This one is the correct option A. Okay. All right. So let's see what could be the a practical implication of this problem. Let's assume there's a furnace, and we know in the furnace there's a radiation section here where these are all the tubes. Okay, these are all the tubes right here, and there's a convection section. So in the radiation section, we can assume the furnace wall and the flame to be like that black enclosure in our problem, and the process tubes and the process through which the fluid flows, and of course by that process gets heated up, that's a gray body. Okay, so according to Kirchhoff's statement, this for this process from the process tubes molecule, yeah, it absorbs radiation, that means it gains heat, uh, and that must be equal to it emits radiation, it loses heat. It has to be the same. And of course, it depends upon the surface condition and the temperature and the wavelength, right? That, of course, is a totally different discussion. So, as I said, at thermal equilibrium, absorptivity is equal to the emissivity of these of the tube surfaces through which the liquid flows. Okay, and of course, we know this relationship here. That the amount of energy gained by the body, or in this case, the tubes. That is, of course, given by this relation. We all know that. This, of course, comes from this concept right here. So, again, going back, A is the correct option.